Good morning, everyone. In the previous class, we discussed one parameter to calculate the right noise margin. So like right static noise margin we have seen, and then another parameter can also be utilized to calculate the writability, or what is the how much the memory is stable. So for that purpose, we can calculate the another parameter, which is the right noise margin. Okay. To calculate this one, because what I have to do, I have to simply change this input voltage, or right trip point is another parameter. So for that purpose, what I have to do, I have to simply consider any particular logic at Q and QB, and then I need to change this BL voltage after activating the word line and other things. Okay, and once like the word line is activated, and so I need to change this BL from 0 to 1, and once we are changing this one, we will get at some point like Q and QB will cross to each other. Okay, and if they are crossing to each other, what it means, that the voltage at which both the Q and QB are crossing, that voltage is, we call it the trip point voltage. Okay, and now just project that trip point voltage on the bit line voltage, and you will get some voltage reference, and that particular point, we call it the right trip point, and the difference between this VDD and this right trip point, we call it the right noise margin. So this is the second way to calculate the right margin, because we have seen in the previous lecture that there is only one stable point in the during the write operation. If we are doing some hold operation and the read operation, in that case we have two stable states, but while writing we have only one stable state. So it is like, suppose if we are performing some Monte Carlo simulations or other things, in that case like to calculate this noise margin is somewhat difficult, especially in the single stable points. So to avoid that problem, the another parameter can also be used to calculate the right trip point or the right margin. Okay, so the right trip point is another way to calculate the right stability. Okay, there is another way to calculate the right margin or the stability, and that we call it the word line right margin. Okay, so what this word line right margin is? Okay, so suppose I have a simple 60 SRAM cell, something like that, which we have already seen. Okay, so this is the 60 SRAM cell. Now what I have to do, I have to perform some operations with this one. What kind of operation I need to do? So the first setup, because see here we have a Q, QB, BL, BLB, and the word line. Okay, so these 5 things which you should consider in a particular state. So the first thing, so whatever that you are seeing here in the right side, this is nothing but this is based on the left side inverter. So here we have 2 inverters. So left and right inverter. So let us say it is inverter number 1, and the second one is the inverter number 2. Okay, so for the inverter number 1, if you see here, the bit line is connected to the VDD, the word line is connected to the VDD. Okay, and let us assume Q is equal to 0. Okay, and or any other thing. It's not like it's just a storage node. Okay, so the first thing what we have to do, because to calculate the word line right margin, on the left hand side of this memory, for the inverter number 1, the setup should be in such a way that bit lines should be connected to the logic 1 and the word line should be connected to the logic 1 for this transistor. Okay, now what about the second inverter? If you see the second inverter, the setup for the second inverter is something like this. Okay, setup for this second inverter is what this VOL is, I will tell you. Okay, so this is the second number inverter. inverter number 2. Okay, and this is the inverter number 1. Okay, and if you see here, the bit line bar is connected to the ground. Yes, because we are doing write operations. So the bit line and the bit line bar are complementary in nature, right? So for write, it's fine. But there is a slight change here. What I have to do, I have to make both the word line for these two access transistors independent. Like I have to fix this word line with the VDD because we are doing some write operation. So the word line, ideally the word line should be connected to the high so that the access transistor will be in on state. Okay, but what we have to do, this first M5, the word line will be VDD, but the word line of M6 will be the controlling parameter here. Okay, so this is the setup which we have to do while calculating the word line right noise margin. Okay, so let us try to see how the waveform will look like. So the first waveform, which belongs to inverter number 1, okay, which belongs to inverter number 1 in respect of Q and QB. Okay, Q and QB. So what I am considering, let us consider initially QB is equal to 0. Okay, so if initially QB is equal to 0, and if I'm changing the QB from 0 to 1, then what will happen? Let us try to see. So let us assume I'm changing this QB from 0 to 1. Okay, so the Q will, because initially the Q was at logic low. Okay, here if you see here at this point, the Q is at logic low, so the QB will be at logic 1, right, at logic high, and the vice versa happens. Okay, so what happens if we have the characteristic something like that, then the behavior will look like this one. Okay, how the behavior will look like, let us try to see. Okay, initially it will be high, and it is something like this. The behavior is something like this. We know that for the right margin, we cannot get complete 0 because I just already told you in the previous class. Okay, so there is a slight potential difference over here. Okay, this one, and this potential difference, we call it the VOL. This is nothing but this is the VOL. Ideally, VOL is nothing but the output lower voltage, like so this VOL, ideally it should be 0, but because we have seen during the read operation, we cannot make it 0. We need to increase the strength of the pull down transistor, so that we can get the lower VOL, so which we have studied. So this is what the VOL is. Okay, so this is what the characteristics of the first inverter will look like, because we have provided the WL. I'm changing the QB, and because the bit line and the word line both are on, so if I will change these QB, then the Q will also be reflected, so the Q will be something like this. Okay, so this is something like the behavior whatever we have plotted over here. Okay, now let us talk about the second case in the second inverter. Okay, how the second inverter will behave and how it will look like. Here, because we have to match the axis, so I need to put WL in the x-axis, because here the WL is the controlling parameter to calculate the word line noise margin. Important thing is here, like this VOL is nothing but this is same as Q, because the Q becomes here at logic low, and I'm assuming that ideally this VOL should be 0. Okay, so sometimes you can consider it at 0. Okay, but because but if you want to calculate the actual word line right margin, so first you have to calculate what is the VOL of this first inverter, and then this voltage should be something like that. Okay, so this VOL comes from there. Now what I have to do, I have to change the word line. So this should be like Q. This is nothing but this node voltage. Input of inverter number 2 is Q. So this is the inverter number 2, and the input of inverter 2 is Q. So this should be connected to Q, but we will connect it to the VOL ideally the VOL and Q will be same if I'm assuming that it will shrink to ground perfectly. But ideally it is not possible. Practically it is not possible. There is some gap because of the transistor mismatch here. Okay, and we can increase the time. Yeah, please.
So the VOL, like first inverter, I got that QB is input and Q is output. So we are getting that graph. But in second, sir, the why VOL and Q we are considering same?
Which one? Yeah, because this graph, purple graph is for Q, right? We are
Yes,
we are changing QB and we are observing Q, and Q becomes the VOL. Okay,
how,
that is
sir?
why. Huh?
It's like how is that?
See here, if we change the, like, if we rotate this graph, so what we are doing here in the first graph, we are changing QB in X. Yeah, let me write in the other way. This is QB and this is Q, and QB is changing from 0 to 1, and I am observing Q just like this. Yeah, so this is how the waveform is. Just I have rotated it in the other way. Okay, and this is the
Yes, sir. Yes, sir.
VOL is. Okay,
Yes,
so
sir.
this VOL is like, so this graph, whatever the VOL we are observing, this is for Q, not for QB. Okay, so that is why I'm considering in place of Q, VOL. You got the thing?
Sir, like VOL is how much Q is above 0, right?
Yes, yes, yes.
So means like
Yeah, so ideally, see, during the in the previous class we have studied like this is this will ideally during the hold operation we can get the perfect swing, something like this, but during the read operation we are not getting the complete. There is something like this kind of characteristics. Okay, so there is some gap because of the transistor mismatch, because of the involvement of excess transistors. Okay, so they cannot, so they are responsible to pull it somewhat above than the ground. Okay,
okay, sir.
so
Okay, means we are considering the lower end of this graph, so
yes,
Q equal to VOL.
yes, yes, yes. Okay, ideally, see, ideally what should be the graph? Ideally we are observing that even during the read operation it should be something like this, but it's not like that. So ideally we can keep this at the Q, and Q is nothing but it is grounded. So but practically if I have to calculate, I have to consider what the VOL is for the inverter number 1, and accordingly we have to set up for to calculate the second graph. Okay, point is clear?
Yes, sir, it is clear.
Fine. So now like the input of the inverter number 2 is the VOL, which we observe in the first graph. And now what I have to do, yeah, this QB is nothing but it is high. Okay, so because it becomes high, so this will be high and this will become the VOL. Yeah, so QB will become 1. Now what I have to do, I have to change this WL of the second number inverter. Okay, like second side of this inverter. So WL I'm changing, and I will observe the Q change, because the WL will change. In that case, might be it will charge because the PL is, this BLB is grounded. BLB is grounded, so this QB will change. Okay, because it will get path to discharge it, because here initially the QB is equal to 1, but through M6 it will get some path after some time, because we are changing this WL of these M6 transistors. So it will trip somewhere here and there. Okay, based on this threshold voltage of this transistor M6. Okay, so let us try to change it, because I am changing this WL word line, and initially this QB was high. Okay, so initially the QB was high over here. So let me try to draw the diagram for that. Okay, yeah, no problem. So what will happen? Initially it will be high, and that will change somewhere here in there, something like that. We'll observe something like this. Okay, now what I have to do, the second thing, next thing I have to do something like that. I have to match whatever the VTL we have observed here. VTL is nothing but this is the lower threshold voltage. Okay, this threshold voltage. So I need to match these two things. Okay, the perfect matched transistor will give like the equal one. Okay, so let me draw it perfectly, so that will be better. Something like that. See, it's not necessary that it is it should be matched to the same point. Okay, so like the crossing of the second curve should match with the crossing of the first curve. It is not necessary. Okay, so you can make it any value. It's not like you have to consider the crossing of both one. Okay, so yeah. So to better understand, let us try to
So
consider the
QB and
different.
WL, characteristics will be inverter like?
Which one?
The QB and WL.
See, because see here, initially, if the WL is equal to 0, okay, initially, because here at this point, WL is equal to 0, okay, WL is equal to 0 means the WL of M6 is equal to 0, and QB is at logic 1, okay, and BLB is at logic 0, okay, this is the initial condition. Now, what I am doing, because the BLB is equal to 0 and the QB is equal to 1, so initially the QB will be high. This is fine. Now, because I am increasing this word line, so because the discharging of this QB depends on the activation of this transistor M6. Okay, so if the M6 is in the off state, this QB will not discharge through this BL. Okay, but after, like, if I'm keep on increasing this word line, at some instant of time, this M6 will be activated, because it will get sufficient gate voltage to make it in the on state. And once this is in on state, this QB will start discharging through this path, and that is why the behavior can turn like this. You are getting the point? Okay, so this is how we will observe the behavior at QB when I will change the WL from 0 to VDD. Now what I have to do, because see, the maximum limit at which we will observe, yeah, this is a really very important point to consider, right? So we can think about this one. So what I have to do, the point at which it was crossing in the first graph, match that point in the second graph, which is here. Okay, so what I have to calculate, I have to calculate this point something like this. Okay, so this voltage is the VWL, word line voltage. Okay, so trip voltage, we can call this one. Now, and the maximum limit here, that will come like this waveform. The WL which we can increase, this is nothing but this is equal to the VDD. Okay, so this is the maximum value of VDD which we can change. So here is some graph. So here is some point which is the VDD, which we can increase the WL. Okay, now what I have to calculate, the difference between these two things. Okay, so this one, the difference between this VDD and this voltage, we call it word line right margin. Okay, so this is how we calculate the word line right margin. So the word line right margin is nothing but this is the VDD minus VWL, and that is what we call it, the word line noise margin. So this is another parameter to calculate the right noise margin. So is there any doubt on this graph? Anyone? How we can calculate it? So this is some important thing. Okay, so why we are considering the different setup for the right margin calculation? Because for hold and for read, we have only one which we can consider, like based on the butterfly curve. Yeah, there is another approach which we can use, like which is we call the N curve, but I'm not teaching N curve here because that is somewhat advanced level. So might be in the next semester I will consider that N curve and other parameters. Yeah, many parameters I have not just taught in this class, especially for the memory design. But yeah, some of the important parameters I'm teaching here. So for the read and for the hold, we can calculate the margin based on this butterfly curve. Of course, for the right margin, we can also have the butterfly curve, something like that. But we have one stable point in the right margin. We have seen in the previous class. So and that is quite difficult, like little bit difficult to analyze the noise margin. So to overcome that problem, we can either calculate the right trip point. We can use the right trip point to calculate the right noise margin, or the word line right margin can also be considered to calculate this one. So these are the two different parameters. Now, because if we have a memory, then while reading or while writing the data, might be it will take some time. Okay, it is not like if we have connected the bit line and the word line, immediately the data will be written, or we can directly read the data. Okay, so the memory itself will take some time, because it is a combination of transistors, and that the transistor delay can there may be some transistor delay, right? So because of that, while reading and writing, while accessing the data, like see, access time is nothing but it is the delay. Why we are calling here the access time? Access time means, like, because we are while reading, we are accessing the data from the storage node and to the sense amplifier, and sense amplifier will decide, like, what is the what time it required to read the data. Similarly, while writing the data, how we can successfully write the data on the storage node of the memory. So because we are accessing the data from here and there, so that is why we can call them the access time. But yeah, we can also call them the read delay or the write delay. Okay, so suppose I have memories, and yes, another thing is, like, I have to calculate the power. What is that power? That is also very important. Okay, so the power is also important. Like, if the memory is in hold state in the read, in the while reading or while writing, it may dissipate some power. So I will tell you how the power can be calculated. Okay, so suppose here we have a memory, and here we have a two storage node in the bit line and bit line bar. So the first parameter which I have to calculate is the read delay, or we can also call it the read access time. What is that read access time and the read delay? Let us try to see it. Okay, so the read delay is nothing but the time at which this bit line discharge to, like, suppose, see here, for example, I have connected, like I just told you, while reading the data, I have to precharge these bitline capacitors. Okay, so we have a two bitline capacitors at the both the ends. Let us assume this Q is 0 and the QB is 1. Okay, this is what we have considered. Now what will happen? I just told you before, we will connect a sense amplifier between these two bit lines. Okay, so yeah, sense amplifier was not in my scope, but yeah, because I think you need to understand how the sense amplifier works. So I will tomorrow I will teach about. I will consider this sense amplifier as well. Yeah, so this sense amplifier is connected between the bit line and the bit line bar. We have two bit line capacitor which are initially charged. How it get charged, I will also explain tomorrow. How these bit line are activated, so that I will tell you. So once these bit line capacitors are charged, then what I have to do, because I have this Q is equal to 0 and the QB is equal to 1. So this bit line capacitor will discharge through this transistor M5 and M1. So this bit line, so this CBL will reduce, but this CBLB will remain same. CBLB will not change, but CBL will reduce. So initially both the capacitor were at the VDD. Okay, but this CBL is discharging somewhere. So the time at which this CBL, this capacitor, the capacitor on the side where the storage node is 0, right? So if this is the Q is 0, then I have to consider the CBL, and if QB is equal to 0, then I have to consider CBLB. So any of the capacitor can be considered. So simply I am saying, like, the time at which this the capacitor discharge to VDD minus 50 millivolts. So if the voltage reach up to this voltage, once we have activated the word line, after activating word line, that the time taken to reach up to this voltage is known as the read delay. In other words, let me say again what I'm doing here, how we are calculating the read delay or read access time. Simply I have to precharge both the transistors, so both the capacitors, like the BL and BLB will be at logic 1. Now because if I have to do the read operation, I have to activate the word line as well. So once I have activated the word line, the counter will start. Now this CBLB will start discharging because the Q is 0 here. CBLB will start discharging and it will reach up to some voltage. It will take some time to reach up to VDD minus 50 millivolt. Okay, so the time taken to reach up to this voltage is known as the read access time. Okay, so the time at which we have activated the word line and the time at which we are getting this CBL is equal to VDD minus VTS, and this time difference we can call it the read access time. Okay, now someone may ask from where this 50 millivolt kind of magic number comes. Okay, so this 50 millivolt means like the sense amplifier that can detect the difference between two potential. Minimum voltage is like 50 millivolt. So if the 50 millivolt minimum voltage difference is there, then the sense amplifier will perfectly sense the differences. Okay, so because the sense amplifier is deciding what data is stored at the storage node Q and QB. Okay, so we need to check the sensitivity of this sense amplifier, like what minimum voltage it can sense. So the sense amplifier, the property of the sense amplifier is like it can sense up minimum 50 millivolt. So at least the 50 millivolt difference should be there between two capacitors. So that is from where this 50 millivolt comes. Okay, so this is how we can calculate the read access time. Okay, yeah, similarly, like suppose if the QB is equal to 0 and the Q is equal to 1, so this we have to consider, like we have to consider this discharging of this CBLB. It's not that much difficult actually. Okay, now the second parameter is the write delay. Okay, what is the write delay? Let us try to see it. Okay, or the write access time. So the write access time, there is two important things that we should consider. Okay, what is the write access time? The first thing is like, suppose if I am writing 0, okay, then the access time could be different, and while writing 1, the access time could be different. Okay, so let us talk about the writing 0 or writing 1, simply anything. Okay, if I am considering the write 0, so the write 0, for the write 0, it is the time when the node Q, like initially, let us assume initially, yeah, let me remove something so that. Okay, let us assume initially this Q was this Q was charged to, this Q was 0 and the Q was 1 and the QB was 0. Because I'm performing write 0 operation, so I need to consider opposite case, because 0 was there and then again I'm writing 0, so there will be no time, right? So I need to change the state, because if I want to calculate the write 0 delay, in that case I have to first make this Q is equal to 1, then I have to write 0 on node Q, because whatever this the term I'm saying, these all write 0 and write 1, these all are with reference to the storage node Q. I have already told you. Okay, and QB is complementary to this Q1. So I whatever the terms we are here, we are referring to the storage node Q only. Okay, so write 0 means we are writing 0 at storage node Q. Okay, fine. So suppose I want to write 0 on the storage node Q. So initially I have considered this Q is equal to 1. Okay, Q is equal to 1 means it is about the VDD. Okay, so it is the time when this node Q reaches to 10% of its initial value. Okay, so whatever the VDD was there, so means it will discharge, like we have to discharge this Q to make it logic 0. Okay, so the time taken to reach up to the 10% of this VDD. Okay, so 0.1 times VDD. So whatever the time it takes to discharge up to this value is known as the write zero delay. Okay, or simply 10% of its initial value if I'm writing 0. So while writing 0, I have to calculate what is the time taken to reach up to 10% of its initial value. Initially, the value at Q was 1. So the 10% of this Q will be like 0.1 into VDD. Okay, so this is what how we can calculate. So how we will do that? Because I have to initially, let us assume initially the Q was at logic 0 1, and I want to write 0 over here. So the BL I should connect to 0, and the BLB will I should connect to 1. Okay, now what I will do, I will activate this WL. So the time at which I have activated this WL, because the BL and BLB are connected. Okay, now I have to activate these access transistors. So the time at which I have activated this WL, this node like this node Q will start discharging. Okay, or the second node will start charging. Okay, then I will just note down at which the value of this Q becomes the 10% of 1 or 0.1 volt. Okay, whatever it is. Okay, so then that time difference is nothing but the write 0 delay. Similarly, right, what is the write 1 delay? Suppose initially I have logic 1 stored at Q, and logic 0 and the BL will become 1 and the BLB is equal to 0. Now the time at which I have activated this word line, and then I will note it down, because initially sorry, I need to consider Q is equal to 0 and the Q is equal to 1, and I want to write 1 at the storage node Q. So the time taken to reach up to 90% of its value. Initially it is 0 volt. Okay, because the Q is equal to 0. So simply time taken to reach up to 90% of its value is we can call it the write 1 access time. So 0.9 times of the VDD, or the 90% of its value, 90% of original value, initial value, something like that. Okay, so this is how we can calculate. Is there any doubt on the delay part or on the access time, how we can calculate it? So one thing you should remember at this point is, like, first you have to initiate the bit lines, then you have to initiate the word line, because you need to precharge this bit line capacitors. Like like suppose I have to perform the write operation, and like I want to perform write 1 at storage node Q, then I have to charge this BL to 1 and the discharge BLB to the 0, right? So first we have to do like that. Otherwise, once you have activated the word line and then you are trying to charge this BLB and BLB, so the time taken to charge this BL and BLB will also be included in that one. Okay, so we do not need to consider that one. So the important thing is, first I have to charge, or I have to activate this bit line, then I have to activate the word line, and then I have to calculate the difference between the time at which the word line was activated and at the time where we are getting the 10% or the 90% of its value. Okay, so we always refer with respect to the word line. Okay, so this is all about the access times which we can consider over here. Is there any doubt on any of the access times? So if there is no doubt, let me continue with the power, how we can calculate the power. Okay, these are some of the essential parameters to calculate, to measure the performance of memory, right? So that is why I'm considering all those things. Now let us talk about the power. Okay, so let us talk about power, how we can calculate that power. The first power is the leakage power, or we can also, leakage power means suppose if memory is on hold state. Okay, so this is with reference to like when the memory is in the hold state. So basically this is nothing but we can also call it the hold power. Okay, hold power is nothing but, like, suppose if the memory is in hold state, so M6 and M5 will be in the off state. Okay, and this both the inverter will, like, they will form a latch. Okay, and if they form some latch, let us assume Q is 0 and the QB is equal to 1. Okay, so because the Q is equal to 0 and 1, there is a power dissipation, there is a leakage power dissipation of both the inverters, like this inverter and this inverter, because both the inverters are like one of the transistor in both the inverters works, and at the deep micron technologies, this leakage current component is more, right? Like, so leakage power dissipation is a serious challenge. So in that case, what I have to consider, whatever the power dissipation is there through this latch, whatever we have formed here, that we call it the hold power. During the hold, whatever the leakage current is flowing through it, we have to calculate it. Okay, so this is what the hold power is. So whatever the power is drawn by the supply voltage during the hold operation, that we call it the hold power. So on the cadence tool, you can directly measure, like if you have the supply voltage, then you can just put all these combinations for BL, BLB in the word line, and then see whatever the power is, this supply voltage is drawing, right? Something like that. So you can directly calculate it. So this is one of the
very small, right? Because it will only be 2 inverters and only one inverter is switch on.
Both the inverters are in some of the status. Let us try to see it.
Okay,
See
sir, means
here.
like if suppose M3, if M3 is on and M2 is off, sorry, M3 is on and M2 is on, then rail to rail, like that.
Yes, see here what happens. Let us assume the Q is equal to 0. If Q is equal to 0, then M4 is in on state and M2 is in the on state. And here, because the QB is equal to 1, so this is on and this is off. Ideally, what is there? There is no path between this VDD and the ground here. There is no path. So ideally, the leakage power dissipation should be 0. But what happens, because at the deep micron technology, there are some subthreshold current flow. Okay, there are some subthreshold current flow because this transistor is off, so the perfect current will flow here. Resistance is 0, approximately 0. On resistance are very less. But if you see this transistor M3, even though it is in off state, some gate leakage current and some subthreshold leakage current will come into the picture, and they will be responsible to draw some minute path between VDD and the ground, and because of that, power dissipation will be there. Yeah, the next scope, like in the next week on the Monday, I will discuss about the different kind of power dissipations and their sources. Okay, so I will discuss all these things, whatever I'm saying, like gate leakage current, subthreshold leakage current. So these all things will be discussed there. Okay, so in detail, I will talk about this power dissipation. But for now, let's just try to understand there are some subthreshold leakage current which will flow even though the transistor is in the off state. And because of that, we will get some path. And then because of that, the power dissipation will be there. Okay. So, so during this operation, we will there will be some power dissipation, and we can call it the hold power dissipation. So I just told you, just because if you have made a latch and you have stored some logic, okay, let us assume Q and Q is equal to 0 and the QB is equal to 1 is like at Q 0 is stored and at QB 1 is stored. In that case, I need to check whatever the power this supply voltage is drawing, then you can calculate the leakage power dissipation or simply hold power dissipation. Another way to calculate the leakage power dissipation is what I have to do, because yeah, see this one and this one is same, like, so we can also make something like this. Okay, instead of individual grounded, I can make something like this. Okay, now what I have to check, I have to measure whatever the current that is flowing here in this direction, because some subthreshold current will flow so through this path, and some current will also flow through this path, and they will sum up at this particular point, and some current will flow from VDD to ground. Okay, first path is this one and the second path is this one. Okay, so I have to find the current which is whatever the flowing through this circuit, and that is how we can calculate the leakage current. So this is what we will get, the leakage current, and then multiply with the VDD, so we will get the leakage power dissipation. Okay, so this is the second way to calculate it. Okay, in reality, in the simulation tool, how we can do that? For the first thing, I have already told you, just you have to calculate the whatever the power this supply voltage is giving. So that is what the whole power we can calculate. But if I have to calculate the leakage power in the second way, which I just told you, then what we can do, we can simply just let me make it again. So I just told you, because whatever the current is flowing through this one is the leakage current, okay, I leakage. But on the simulation tool, how we can do that? To do that, we have to simply connect a voltage source in between, okay, with 0 volt, okay, and then we have to check what is the current is flowing. Yeah, there is no potential difference, there is no voltage drop across this source because the voltage source is 0 volt. And then I have to calculate the current. Directly you cannot calculate the current through the wire. You have some, either you can have some so in the simulation tool, directly you cannot calculate the current through the wire. You can just calculate the current through the transistor or some of the devices, okay. So that is why you need to connect one 0 volt supply voltage or the voltage source between this node and the ground, and then now you can calculate whatever the current is flowing through this voltage source, because the voltage is 0, so the potential difference is 0. So whatever the current it will come, that will be the same as like what we made the concept before. So this is how we can calculate the I leakage. Okay, so this is how the I leakage current can be calculated. So these are the two ways to calculate it. Second thing is the read power. How we can calculate the read power or read leakage current? If I am doing some read operation on the memory, in that case, definitely there will be some current flow. Okay, so what current will flow? Let us try to see here. Let us assume the BL is equal to 1. So because I am reading the data, so in that case, BL will be 1, BLV will also be 1. And let us assume I have 0 which is stored at Q and the 1 which is stored at QB, and the WL is equal to 1. In that case, the bit line capacitor will start discharging. Okay, so if these there will be some capacitor at this point and there will be capacitor at this point as well, something like that. Okay, so what will happen, because the Q is equal to 0, so this capacitor, BL side capacitor, will start discharging and the path will be M5 and M1. Okay, so whatever the current that is flowing through this path, that we call it the read current. Okay, and the read current and multiply with the supply voltage or whatever the maximum voltage we have, that you will get the read power. Okay, so to calculate the read power, simply I have to calculate whatever the current is flowing through M5 and M1. Okay, and accordingly we can calculate the read current and then the read power just by multiplying with the supply voltage. So this is how we can calculate the read power. So this is easily doable. So because see what I have to do, because this path is not activated. Suppose Q is equal to 0 and the QB is equal to 1. So this read path is not activated. Only the first, like M5 and M1 is activated. So what I have to do, I have to simply connect a So simply I have to calculate the current which is flowing over here, and that is the leakage power. But on the simulation tool, what I have to do, before connecting this ground, I have to connect a voltage source of the 0 volt and then ground it. And now I have to find the current which is flowing through this one. So this is what I have to do on the simulation tool. Okay, and we can calculate the read current. Similarly, the third kind of power could be the write power. So while writing, how we are writing, the two transistors are in on state, this and this one, either this and this or this and this one. So because we are writing the data, so the current flowing through this and this, whatever the current is flowing, that we call it the similar kind of setup we have to use it, right? So so the write power can be calculated. So this is all about the different kind of the power dissipation that we need to calculate, and the different kind of delay which we can calculate for the memory. So these parts, whatever I'm just teaching in this particular slide, is really very important, especially if we are planning to do some research on the memory side, right? So these parameters are mandatory to calculate. Okay, so where is the research? Now the question is, where is the research?
Sir,
Yeah, please.
Sir, in write power, on one side there will be charging. Suppose we are writing 1 to node Q, then on one side there will be charging of 1 to Q, and one side there will be discharging. So both
Yeah,
we have to add a watt as power.
we already need to consider the node Q only, right?
We already need to consider the node Q.
I just told you before. On the Q side. Yeah, so there could be two power while writing 0 and write 1 power. So the power could be different in both the cases. Okay, and here the another kind of research comes, like might be there could be like the write delay and the write 1 delay, both could be different. Write 0 power and the write 1 power, these both could be different. Okay, so if both are different, so I think I don't need to say to you, because yeah, this is because uh, attacker can attack on the memory based on the leakage power analysis. If the different kind of the delay or the different kind of power is there, so attacker can see whatever the power the memory is drawing, and accordingly they can judge whatever the data is. Yeah, from security perspective you can do like that, but yeah, this is not in our scope, so I'm not teaching. But in the next semester we'll talk about this one, how the different power or the different delay play a major role, especially on the security perspective of the memory. Like, so we can see later on. Yeah, so well said. Like the write 0 power could be different, write 1 power could be different, and we can calculate both things. Okay, so this is all about the power dissipation through the memory and the delay in the different cases. Okay, any other doubt on this access time and the power side? So I think it's clear, not that much difficult, so you can do it, right? So it's not that much tough. Okay, now let us move ahead because we have only 2 minutes of time, so we cannot calculate, but we can see this one. If we have a 60 SRAM cell, something like that, and I want to make the layout of this one. So like, see, because if I have to fabricate the chip, I have to make the layout, physical design of this one, and the physical design can be that, like then we can like once the physical design is ready for all the circuits, whatever we are planning to fabricate it, then we can fabricate it, something like that. So here, this is the layout of, yeah, the layout is nothing but this is the advanced version of the stick diagram, which we have already studied. Stick diagram is, there is no just a rough estimation of the layout is the stick diagram. But here, if we are following all the design rules, then the layout will look something like that. Yeah, we have already studied what the design rules are. Okay, so after following all these things, we can make the layout of 60 SRAM cell, something like that. Okay, so just to see this, here all the transistors are here. So the layout is also important, like see how you are designing the layout and whatever the size of this complete cell is. Like see here, if you are designing without following all the DRC rules, like the distance between these two is not following, you are making like your this distance is more, so it will require more area. So while designing the layout of any circuit, the proper design rule must be checked, and the minimum size, like it should be as small as possible, and that must follow all the rules. Okay, so the two condition is, right, the design should be as small as possible, and the second thing is none of the design rules should be violated. Okay, so all the design rule must be it should pass through all the DRC check, and the minimum should be, the size should be the minimum. So the proper arrangement of transistor, it play a major role. So for that, the stick diagram is the important thing. So first make the stick diagram of all the circuit, whatever we have, and then convert it into the layout, and that is, we can make it. Okay, so this is what the layout of 60 SRAM cell is. Yeah, so these are some of the terminal where this is M5 and M6. We have connected the word line over here. If you see M5 and M6, and the other terminals are BL and BLB, and the Q and QB nodes are there. So this is how the layout of 60 SRAM cell will look like. Okay, so I think we do not have the time. So this is for that's it for the today's lecture. Tomorrow we'll discuss about the the memory architecture. Like, see, till now we have discussed a single cell, like single bit storage element. So on this SRAM cell we can store a single bit. Okay, but if I want to store more large number of information, like the more number of bits, in that case we need to come up with the architecture. Okay, so in the tomorrow's lecture I will discuss about what should be the architecture and what are the different other peripheral blocks needed for the memory. Okay, so and then also like sense amplifier, I will discuss about the sense amplifier, how it works, and how it detects the difference between BL and BLB while reading the data. Okay, so this is what we will see in the tomorrow's lecture, and we will finish the memory part by tomorrow. And the next week we'll talk about the power dissipation. So thank you so much. I'm closing the session here.